Hi, this is Tony and Ian. Yes.
We're hiding out here at a coffee shop. They don't know we're here, but be done quickly.
What are we going to talk about here?
Well, we're going to show you one more demonstration of the fast Fourier transform, the FFT.
Yeah, because in our last video we promised a demo.
We did, and
right?
we want to deliver. So we've got some footage from a live demo we did last year at the Access Academy talking about instruments.
That was a lot of fun. And instruments, when we talk about wait, I got an instrument. A piano?
Yeah, that's actually the kind of instrument we're talking about, measurement instruments together with musical instruments.
Oh, and how they work together and how you can see musical stuff on this.
Because the different sounds that you hear correspond to the different shapes that you see, and we found that a useful way to introduce the concept of the frequency transform to a new audience.
That sounds great.
All right, let's check it out. So we mentioned music a second ago. We're going to do another scope demo now.
And this is really cool, another demo.
A sound, before you hear it, coming out of a band on stage was at some point an electrical signal in a wire. And so, of course, we can see those same kinds of things on the scope. And the shape of what we see on the screen is related to the type of sound that we hear. Imagine drawing a graph of every key on the keyboard. So now our x-axis isn't time anymore. We're drawing a graph, but now the x-axis is pitch. And you guys remember what the alternative word for pitch was from a few pages ago?
Frequency.
Frequency, yep, exactly. So now the x-axis is frequency. And if any note is not being played right now, it's going to have a very, very low voltage. And any note that is being played will have just one little spike there.
Imagine this being the sine wave that we were showing you earlier. And now what we're doing is we're turning this thing on its angle like this. So imagine looking down this way and you're seeing the spikes kind of in this form here. It's taking the same signal, but we're just looking at it a little differently.
And so this operation is called a frequency transform, and the scope can do it. So can we do the A440 again? So I'm going to turn on math and hit FFT, which stands for fast Fourier transform. And it's not a perfect sine wave, so there's other credit here. But you see there's one big spike here. And if she adds another A an octave above that one, you'll see two big spikes here. And these are at 440 hertz and 880 hertz. I could probably...
You turn that down a lot.
Yes.
So this is nice about the oscilloscope. You can see both views at the same time, but we're just going to show you the new one that we're talking about.
So now can we try playing, let's say, a C chord or something? So we see these three main spikes. They're really, really close together. In fact, they're too close together for the instrument to tell them apart unless we change some other settings. So let's go back to the single note again, the A440. This nice one big spike. What happens if we change instruments? What do you guys think will happen here in the frequency view?
I think there'll be a more definite spike and like smaller secondary spikes.
So this one's a square wave in, and I'm going to turn on, just so we can see, there's what it, can we hit that one more time? So there's the square wave, and I'll turn it back off. So we can actually see that that main spike is there, but these other spikes have actually gotten a little bit taller. And there's a really, really strange reason for that. You can think of any shape in there as a bunch of different sine waves added together. So this gets right back to that question you were asking about, is there a way to mix different signals together to get a more complicated one, right? And if you build out of sine waves, there's exactly one way to do it. If we took this sine wave and added to it something like this sine wave, we get, so now we will add another one that's even shorter and wigglier, smaller voltage, higher frequency, and now we'll get something like, and you can see how we're getting, the more of these we add in, the closer and closer we get to a square wave. So it works both ways. You could think of being able to break a really complicated signal down into these little pieces, or you could think of a way to take lots of little sine waves and build a really complicated signal out of it. And another way of thinking about a frequency view is, what if you had
I thought was really interesting.
What if you had a signal at 94,700,000? What if you had a radio signal that was repeating it 94,700,000 times per second? In other words, if it was 94.7 megahertz. And then you might have another one up here at 107,500,000.
107.5, yeah.
Does anybody recognize these numbers?
Wait, those are like the actual, like the radio stations call it, like 107.5.
Exactly.
Yeah,
Yep.
exactly.
So these are the frequencies that their main transmitter is transmitting at, and if we had the right kind of antenna and fast enough scope, we could actually draw this same kind of orange graph of radio stations, and we'd see them all transmitting.
So do you guys understand, like when you go into your radio and you put in your favorite channel, it's actually finding that frequency. And this thing can capture it and find out exactly if it's right or not.
That's it. Our video is over. So for more information about the fast Fourier transform, go to tektronix.com/FFT-basics. All right, everybody.
Cheers.